so this is our AP Chemistry Chapter 6 lesson video part 1. And so I'm going to cover section 6.1 and 6.2. And so hopefully you remember a lot of this from honors because it's electron configuration and a little bit about quantum numbers. And so hopefully that will seem familiar to you. So in 6.1, we're going to talk about kind of the wave nature, particle nature of light. So the electronic structure of an atom refers to the number of electrons in an atom as well as the distribution of electrons around the nucleus and their energies. Okay, so y'all, we're going to focus a lot on where the electrons are, like which energy level, which determines how much energy they have, because how they move or react in a reaction all depends on that. So light. Visible light is an example of electromagnetic radiation. It's just one of many types. All types of electromagnetic radiation move through a vacuum at a speed of 3 times 10 to the 8 meters per second. We call that the speed of light. It's represented as C in a formula. Okay, so our visible light, of course, is broken up into all the colors of the rainbow, but there are other forms of electromagnetic radiation besides just visible light. The distance between two adjacent peaks or troughs is the wavelength. So peak to peak is wavelength, trough to trough is wavelength. Really, any two matching points on waves next to each other can be used to calculate wavelength. The number of complete wavelengths that pass a given point each second is the frequency of the wave. So if you had a point like right here, and you counted how many wavelengths pass each second, that's what's considered the frequency. So all electromagnetic radiation moves at the same speed, namely the speed of light, 3.0 times 10 to 8 meters per second. So since they're all traveling the same speed, if the wavelength is long, there will be fewer waves that pass a certain point, so frequency will be low. And if the wavelength is short, then frequency will be high. So wavelength and frequency are inversely or indirectly proportional to each other. So if wavelength is high or long, frequency is low, because it just takes longer. Remember, we're going to pretend they're traveling at the same speed because they're both electromagnetic radiation. A lot of wavelengths will pass on this top wave because they're really close together. On this bottom wave, since the wavelengths have spread out and the wavelength is longer, just fewer would pass by in the same amount of time. So here is the whole electromagnetic spectrum. So see, visible light is just one portion. You have radio, microwave, infrared, UV, X-ray, gamma ray, lots of different waves. But they all travel at the same speed, so what's different is the wavelength and also the frequency. So our first formula for this chapter is C equals lambda times nu. So C is the speed of light, that's a constant, 3 times 10 to the 8 meters per second. So most likely the question is not going to give you this number. This number kind of needs to be in your mind. Lambda is wavelength. It must be in meters. So you know that a lot of times we like to use other units than just meters. So like if it's in centimeters, you would need to change it. If it's in nanometers, that's a common one you'll see. You've got to change it to meters. And then nu is frequency. It'll either be in hertz, or a hertz is a 1 over a second. So you'll see seconds to the negative 1 a lot. All right, so first, this one's not a math question, it's just a conceptual question. It says, which wave has the higher frequency? If one wave represents visible light and the other represents infrared radiation, which wave is which? Okay, so y'all, if I look at these, if they're traveling the same speed, a lot more of these waves are going to pass than this one. Okay, so the higher frequency would be wave 2. Then it says which one represents visible light and which one represents infrared. Well, if I look, visible light is here, infrared is here. So what's wavelength doing as we move this way? It's getting longer wavelengths. That means infrared will have longer wavelength. So wave A would be infrared and wave B would be visible. So wave 2 has higher frequency. Wave 1 is our infrared, and wave 2 is our visible. Sorry, I said wave 2 has higher frequency, but I was pointing at 1. Wave 2 has higher frequency because shorter wavelength, and then wave 1 is infrared, wave 2 is visible. Okay, so maybe pause it and try this one on your own. I'll assume you've done that. You may need to look at that electromagnetic radiation slide. So it says if one of the waves represents blue and the other red light, which is which? So if I go back again, I can see that they've pulled the visible out right here. Okay, so remember, as we're going this way, we're increasing the length of the wavelength. So red should have a longer wavelength than all the other colors, okay? And I think it picked between either green or blue. I don't remember the question now. But red is the longest wavelength when it comes to colors of light. So it says which one will be red and which one will be blue. Well, that means wave 1 would be red because it has the longer wavelength. Wave 2 would be blue because it has the shorter wavelength, just like I said right there. All right, so now we're getting to some math here. It says the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. Okay, so this is my lambda. What is the frequency of this radiation? So this is my frequency. Okay, so we know that our formula is C equals lambda nu. I'm trying to solve for nu, which is my frequency, so of course I just divide lambda to the other side. So it's going to be C divided by lambda. But the problem is, I told you, lambda has to be in meters. They gave me nanometers right here. Okay, so I'm going to need to convert. So I have 589 nanometers. So of course, golden rule says nanometers goes on bottom, and we know that the 1 always goes with the prefix unit. My power for nano is 10 to the negative 9, and that's meters. So once I do that, I get 5.89 times 10 to the negative 7. And now that is meters. So that's a number I can plug in. Okay, so now I'm ready to plug in. So notice the question doesn't reference C at all. You just got to know C. So it's 3 times 10 to the 8 meters per second. And then over my wavelength, which we changed to 5.89 times 10 to the negative 7 meters. So my meters cancel. Once I divide, I got 5.09 times 10 to the 14. And this is where you got to be careful. Meters cancel, so you'll see we're left with seconds, but seconds is on the denominator. See how it's meters per second? Seconds is the denominator, so you can't put seconds. You have 3 options. You can put seconds to the negative 1 because it's in the denominator. You can put 1 over second if you want, or you can put hertz. Any of those work. I'll go ahead and tell you on AP stuff, I usually see seconds to the negative 1 most commonly. Okay, but any of those would work, but just seconds will not work. All right, so hopefully that one wasn't that bad. We did this exact question in Honors Chem, actually. I have it on my Honors Chem PowerPoint. All right, so y'all pause it, try this one, and then we'll look at it together. So it says, a laser used in eye surgery to fuse detached retinas produces radiation with a wavelength of 640 nanometers. So there's my wavelength. It says, calculate the frequency of this radiation. So in other words, we're just doing the same thing. So we know C equals lambda times nu. I'm trying to solve for nu. So I'll move lambda to the other side. And I'm going to rearrange quickly because y'all should know how to do that. All right, so the problem with my wavelength, again, is it's in nanometers. So I take my 640 nanometers. I know golden rule says nanometers goes on bottom. The prefix unit always has the 1. The power for nano is 10 to the negative 9. So once I multiply, I get 6.4 times 10 to the negative 7 meters. Once I have meters, I can plug into my formula. Okay, so C is constant, speed of light, 3 times 10 to the 8 meters per second. Lambda is my wavelength, which we determined was 6.4 times 10 to the negative 7 meters. So again, my meters is going to cancel. All right, and once you do that, you should end up getting 4.69 times 10 to the 14. And remember, we're left with seconds, but it's in the denominator. So I'm going to put seconds to the negative 1. You could put 1 over second, or you could put hertz. Any of those is fine. But remember, just seconds is not appropriate for a unit of frequency. All right, so hopefully you got that one right. Trickiest part of this one is just making sure to remember you have to have meters. All right, so our next one, it says an FM radio station broadcasts electromagnetic radiation at a frequency of 103.4 megahertz. So this is my frequency. Then it says calculate the wavelength. So I'm looking for wavelength this time. So we still set it up the exact same way. So C equals lambda nu. All right, I'm looking for lambda, so this time I'm going to divide both sides by nu. All right, the problem is the frequency needs to be in seconds to the negative 1 over second, or hertz. It's in megahertz. Okay, so I'm going to have to convert that. So you may need to get that SI prefixes chart out. I'll go ahead and tell you, I don't see a whole lot of SI prefix conversions on the AP exam, so we'll discuss in class which are the most important ones for you to memorize, but probably don't have to memorize mega. All right, so we start with 103.4, and we are talking about megahertz. So, golden rule says megahertz has to go on bottom. It has the prefix, so I put the 1. If you look at your power for mega, it's 10 to the 6. So once I multiply, I end up getting 1.034 times 10 to the 8 hertz. Okay, and remember y'all, hertz is just seconds to the negative 1. All right, so I'm ready to plug in. So C is, of course, speed of light, 3 times 10 to the 8 meters per second. And my frequency is 1.034 times 10 to the 8. I'm going to put 1 over second over here just because it helps some of y'all see that seconds cancel. So see how seconds cancel right there? So what I'm left with is meters. So once I divide, I got 2.90 meters. Just like that. All right. So again, now all of this is basic plug into a formula. Like if you can get plug into the formula questions, you're golden. Okay, that should be something that's super easy for us. It's all those that you can't plug into a formula. Those are the tricky ones. All right, so, whoops, we don't need to do a warm-up. All right, so next we're going to move on to section 6.2. So this is quantized energy and photons. So there are 3 main phenomena that cannot be explained by the wave theory of light. Okay, so light has a dual property that goes along with it. Sometimes it acts like a wave, sometimes it acts like a particle. So these 3 phenomena that light does, they're not backed by the wave theory. So this is when light acts like a particle. So 1 is black body radiation, 2 is the photoelectric effect, and 3 is an emission spectrum. Okay, in honors, we mainly focused on this one, so these other 2 may be kind of new for you. All right, so black body radiation. When solids are heated, they emit radiation as seen in the red glow of a heated metal. So now when you heat metal, it'll start turning reddish or orange or kind of yellow. That's what we refer to as black body radiation. So the wavelength emitted depends on the temperature of the object. So like on this horseshoe right here, back here, where it's not emitting any light, it is a cooler temperature. And then here, as that light is turning yellow, it is a much higher temperature. Okay, and so that can't be explained by the fact that light is a wave. So Planck assumed, remember we talked about him from Planck's constant, Planck assumed that energy could only be released or absorbed in certain fixed quantities that he called a quantum. Okay, so this is where we started talking about in honors, the electron absorbing a quantum of energy and jumping to a higher level, or losing a quantum of energy. So remember, if it doesn't absorb a full quantum, it can't jump. So that brings us to another formula that we talked about in honors, and that's E equals h nu. So in this case, E is energy, it's in joules. H is Planck's constant, it's 6.626 times 10 to the negative 34 joules times seconds, not per. And then nu, of course, is frequency, which is hertz, 1 over second, or seconds to the negative 1. Okay, so frequency is the same. So when you use this formula, you are calculating the energy of 1 photon. That's all you're doing, calculating the energy of 1 photon. So since we're multiplying a number by something that's 10 to the negative 34, your answers are probably going to be super small, and that's okay. All right, so according to Planck's theory, matter is allowed to emit or absorb energy only in whole number ratios of h nu. So in other words, if it doesn't have h nu, 2 times h nu, 3 times h nu, 4 times h nu, it's not going anywhere. Since h nu, like I just discussed, is a very small number, a quantum of energy is a very small amount. Because energy can be released only in specific amounts, we say that energy is quantized. Okay, so that quantum of energy that it has to absorb or release says that we call energy quantized. So, next is photoelectric effect. The photoelectric effect occurs when light of a certain frequency shining on the surface of a metal causes electrons to be emitted from the metal. So what's happening is we have certain frequencies of light shining on a metal surface. So just pretend like this is some aluminum foil. Well, if you get the right frequency, it will eject some electrons. That's not a wave behavior. That's a particle behavior. So in this case, light behaves like a stream of tiny energy packets that we call photons. Okay, so we know light is not an actual particle because it doesn't have any mass, but it behaves like a particle sometimes. So that's where we get photons from, is we say its particle is a photon, which is really just like a tiny packet of energy. So think about like a superhero movie where they can like make a ball of energy in their hands and like shoot it at somebody, but it acts like a particle. Think of photons as that, but they're just super tiny and very small, so they're not killing us when they're hitting us. You know. All right, so let's look at our first one together. So it says, calculate the energy of one photon of yellow light with a wavelength of 589 nanometers. So they gave me wavelength, but they've asked me for energy. So y'all, energy is h nu, Planck's constant times frequency, but yet they only gave me wavelength. So what am I supposed to do? Well, y'all, we already learned the other formula, C equals lambda nu. I can always get in between wavelength and frequency using that formula. So what I would need to do is find frequency first, so then I could plug in here. All right, so I divide both sides by my wavelength. But of course, this is the same sodium yellow light that we saw in the other one, but we'll still redo it. I have to change nanometers to meters. So 589 nanometers, 1 nanometer is 10 to the negative 9 meters. You can remember nano and 9. So it's 5.89 times 10 to the negative 7 meters. So then I plug into this formula first. So C is 3 times 10 to the 8 meters per second. And my wavelength is 5.89 times 10 to the negative 7 meters. So my meters cancel, and I get, whoop, looking at the wrong one, I get 5.09 times 10 to the 14 seconds to the negative 1. Once I have frequency, now I can plug into my energy formulas. Okay, so I know energy is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And I multiply that by my frequency, which is 5.09 times 10 to the 14. I'm going to call this 1 over second for now. You can still call it seconds to the negative 1. I just want to make sure you see that what happens to seconds, they cancel. So I take my two numbers and I multiply, and I get 3.37 times 10 to the negative 19 joules. So just as we talked about on the previous slide, this is going to be a very small amount of energy, 10 to the negative 19. All right, so if they give you wavelength but ask you for energy, you just got to get frequency first. It's not that big of a deal. It's just kind of using two formulas instead of one. All right, so for the next one, pause it, try it, and then we'll look at it together. So it says, let me make sure I'm on the right spot. I did my answer sheet out of order, so I keep getting lost. A laser emits light with a frequency of 4.69 times 10 to the 14 seconds to the negative 1. What is the energy of one photon? Well, y'all got the easy one. All right, so this time they just straight up gave you frequency. You don't even have to use the speed of light formula. So E equals h nu, so then I just plug in. So h is 6.626 times 10 to the negative 34 joules times seconds. And then I just multiply it. They even gave us frequency in the right unit. Boy, this one was easy. I would not expect you to see anything this easy on the AP exam. This one's way too easy. Unless it's like one of 20 parts on a free response question. That's where you get the easy ones. The first couple are usually easy. All right, so then we just multiply, and so when I multiplied, I got, let's see, let me make sure I'm on the right one. Yep, right there. I got 3.11 times 10 to the negative 19 joules. And so again, I got a nice tiny number, which is what I would expect if I'm calculating the energy of one photon. All right, so hopefully you got that one right. So then it says, if the laser from the previous question emits a pulse of energy containing 5 times 10 to the 17 photons of this radiation, what is the total energy of that pulse? Okay, so y'all, when we calculated this number right here, this is the energy in 1 photon. Okay, so I can make that into a conversion factor. I can say 1 photon equals, and this is just our answer from the previous one, I'm just pulling it from right here, 3.11 times 10 to the negative 19 joules. Okay, but we have this many photons. So I just take my 5 times 10 to the 17 photons, and then I put my 1 photon on bottom, and my 3.11 times 10 to the negative 19 joules on top. So photons cancel, and I multiply my two numbers. And so in that case, I got 0.16 joules, just like that. Okay, so y'all, you may think like, wow, I didn't need to write all this out. I knew to multiply. Well, if you just knew to multiply, that's great. It's just every now and then, sometimes y'all guess, do you multiply or divide? If you'll set it up conversion factor wise and follow the golden rule, you'll never get it wrong. Okay, so just do this way if you need to. All right. So then it says, if the laser from, oh, I guess I still needed that. If the laser from the previous question emits this much energy during a pulse, how many photons? Okay, so again, from the previous question, I know 1 photon equals, what did I say, 3.11 times 10 to the negative 19 joules. So this time, I'm starting with 1.3 times 10 to the negative 2 joules. So see, this is what I'm saying about setting it up like a conversion factor. You don't have to wonder like, oh gosh, do I multiply again? Do I divide? You just follow the golden rule. Joules has to go on bottom this time. So 3.11 times 10 to the negative 19 joules equals 1 photon. Because y'all, it asked me about photons this time, so I need the unit photons. So this time I divide. So if you're ever not sure, don't guess whether you multiply or divide, just set it up like a conversion factor. All right, and so once I did that, I got 4.18 times 10 to the 16 photons. All right, so hopefully that wasn't too bad. All right, so let's move on. So, what is light? Wave or particle? Well, like I said, it's kind of both. So y'all know I like this picture. You might remember it from honors. Okay, you can see wave, and you can see particle, P-A-R-T-I-C-L-E. I love that picture. I'm so dorky. All right, so we must consider that light possesses both wave-like and particle-like characteristics. So for example, when it goes through reflection, waves can reflect, but so can particles. So that's a property of both. But for example, when it goes through interference, which is when waves overlap, waves do that, but particles don't. Like two particles can collide, they can't overlap. But light does that. But on the other hand, it does photoelectric effect, which is where it ejects electrons. Waves don't do that, particles do. So that's why we say it has a dual nature, where it's like a wave, but it's like a particle. All right, so, okay, well that's the end of our first video. I was about to keep going. All right, so hopefully you remember a little bit of the C equals lambda nu and the E equals H nu from honors. If not though, we just went right back over it and hopefully you got it now.